Okay, so let's start. Um, Hi everyone, welcome to the 10th week of our NPTEL course. And so this week was mainly on the calculus of variations. By the way, the screen is visible, yes. So, calculus of variation on its face, it's purely a mathematical topic. In fact, they do teach it in the maths department if you are doing math degree. But we know that it's useful for physics, and as we saw at the end we get a Lagrangian equation. Okay, so that is why it's useful to spend some time in this. Okay, so we'll start with recap, but this time we'll also do some problems during the recap as well. Okay, so we started with definition of functional. Okay. In a layman term, it's a function of function, right? Or it could be a function of functions as well. So, example would be, let's say, a functional of f is just integral of f of x dx from 0 to 1. This is one function. Okay. So, for a normal function, your input is some number, real number, or a vector that is a string array of numbers, and output is your function. In case of a functional, your input is a function and output is some number. Okay. So another example which all of us are very familiar with because we have done quantum mechanics is uh, expectation of any operator, right? Let's say energy, where energy is a functional of its wave function. So given a wave function, we can calculate the expectation of Hamiltonian. Okay, so psi h psi. Okay, or if we expand it, it's like psi of x, then h operated on psi of x dx. Okay, or in multidimensional, you would have x, y, z, everything. Okay, so energy is the functional, and you know that the ground state is the function that minimizes this energy. So it's actually useful in this as well. And all, this entire approach leads to a theory called DFT, density functional theory. Of course, we are not going to study that in a classical mechanics course, but it's useful to see that everything is getting connected. Okay, so another functional which we saw was surface area of revolution, which was given by 2 pi integral of dx y square root of 1 plus y prime square. Okay, so this is a functional of y, where y itself is a function of x. Okay, so this is one example. Similarly, you can write volume of y. So for a volume, and it's a or y of x looks like this. Then the volume after rotating it about the x-axis would be go towards it. Let's say we are at the point x, and between x and dx, you have this circular disk. The thickness of this disk is dx and the radius of the disk is y. So the area is pi times y square and the volume would be times dx and then integral. Okay, so this is another functional. And just to give you the flavor of problems that you can do with this, you can consider one special problem that is called painter's paradox. Okay, and the statement is following that the function y is given as 1 over x. Okay, so it's an hyperbola, and now you revolve it around the x-axis, so it looks something like this, right? And then you start with somewhere non-zero value and go to till infinity. Okay, so start with some x0 and you are going with up to infinity. So this shape looks like a horn. It's called Gabriel's horn. Okay, and the question is what is the surface area of this shape and what is the volume? Okay, so let's calculate the volume first. Volume, which is how much you can fill inside. Okay, so that is integral of pi y square. Y is 1 over x square. So 1 over x square dx, right? And you start from x0, go till infinity. So pi integral of 1 over x square would be minus 1 over x, and it's from x0 to infinity. Okay, and this is pi, then minus 1 over infinity, which is the same as saying 0, and plus 1 over x0. So this is pi by x0. Okay, and what about area, surface area? Well, it is given by this equation. So 2 pi times integral of dx, and y is 1 over x, and square root of 1 plus derivative of y square. So y derivative would be minus 1 over x square. This becomes 1 over x to the power 4. Okay. Now this integral is obviously very difficult to do, but what we can show is that it is in fact infinite, and that is what we are going to show. So since this is always greater than 1, we can write that this integral is greater than integral dx and 1 by x, right? We are just removing some positive numbers every time. Okay, and this is equal to 2 pi ln x, where x is from x0 to infinity, which is 2 pi ln infinity minus ln x0, as if it makes sense, but of course it doesn't. It simply means this is infinity, right? So now we have surface area is equal to infinity and volume is some finite. And so yeah, that's the answer. And the paradox, so-called paradox, is that basically if you have a paint and if you want to fill inside it, you can fill it with some finite paint, right? If the volume is say 5 liter, then you just take 5 liter of paint and it will be filled. But if you want to paint its surface, you won't be able to with any finite amount of paint. And that is the paradox. Okay, so let's carry on the recap. So the next questions to be asked in this framework is what kind of curve maximizes or minimizes something, right? And this is similar to the questions that we know how to solve. What point minimizes a function, right? And that answer is simple. It's the point point x star for which derivative of function is equal to 0, right? That is in general minima or maxima. It could be a saddle point as well. Okay. Or if the function is multidimensional, if it can take vector argument, then it's the point x star vector for which the gradient of that function is 0, right? So, but now what we are asking is what function or what curve maximizes a functional, right? And then the answer which we later on found out was something that is called Euler-Lagrangian equation again, and it's a differential equation. Okay, and before doing that, we also saw that if there are constraints, so the problem statement is minimize f of vector x, and this f itself could be a vector function, okay, in general, but let's say it's just some one function, one dimensional function. So input is a vector, but output is a scalar, a function x, where x belongs to some Rn n dimensional space, subject to constraints that phi I of x is equal to 0, where I could be running from 1 to m, right? Any number of constraints. But if constraints should be less than the number of variables, otherwise you have either solved this for x or you have no solutions, right? So every constraint in general reduces the dimensionality by 1. So if you are in n dimensional space, then if you apply one constraint, that means you are in n minus 1 dimensional surface. Then second constraint and you are in n minus 2 dimensional surface, right? So now we want to minimize the function f, but not in the entire space, but on some surface. Okay, this should be reminiscent of what we had learnt in first or second class, where we had some constraints and we were trying to find something about those constraints. Okay, and solution was Lagrangian multipliers. So constructing a function which is a function of all the variables and some auxiliary variables which we call Lagrangian multipliers, and that is given by this function f plus lambda 1 phi 1 lambda 2 phi 2, okay, up to lambda m phi m, and the solution was that gradient of f should be 0, where gradient is supposed to be taken with respect to x1 xn and with respect to lambda 1 and lambda m. So this gradients produce the constraints which we are working with, and then these equations will produce the corresponding solutions. Okay, so we saw one example in which function was x into y, and the constraint was x square plus y square is equal to 1, and we saw two methods, both of them are of course equivalent, but a third method which I thought I should share with you. Not so much of a method, uh, but more of a trick. At least in this case, it works. Is that the constraint is given, right? So in general, x comma y belongs to R2, right? It could be anywhere in the plane. But because of this constraint, now we are on a curve. And what is that curve? That is a circle, unit circle, right? So we have to be on this unit circle. And what is this function f of x, y? That is xy. So what we can do is draw contours of f. Okay, that is the curves along which the value of xy does not change. So what are those curves? For example, xy is equal to 2. That defines a hyperbola, right? Then xy is equal to 1. That is again another hyperbola. So xy is equal to 2 would be something like this. Xy is equal to 3 would be something like this. Xy is equal to 1 would be something like this. And let's keep ourselves in the first quadrant. And uh, clearly the function f is increasing along this direction. Increase, right? Here it's increasing like this. Here it's increasing like this. And now we are supposed to be on this circle. So where in this circle would we have the maximum value of f? And that is when this curve, there would be one curve, one contour which just touches the f, right? And we know that since f is symmetric in x and y, and constraint is also symmetric in x and y, so it has to be at x is equal to y, right? Which means x is equal to y in the first quadrant, and that means x and y both have to be 1 by root 2. Okay, the same argument holds in the second quadrant also. In this case, this would be like -3, -2, and -1. So in this case, this would minimize the function, and this would be the maximum function. Okay, same thing here and here. So these two would be the minima, and these two would be the maxima. Okay, so this was first quadrant. Okay, and clearly the method of Lagrangian multipliers does exactly this and gives the same answer. Okay, and then we uh, came to the final problem, the mean problem, which was that given a functional g of y, okay, and that is given in terms of an integral of some other function f, okay, from x0 to x1. And the question is which y, which curve y extremizes, which means either minimizes or maximizes j, right? And this is a very sensible question to ask because the different functions would produce different values of integrals, and there must be some curve which kind of either gives minimum or maximum value, right? So, and then we say the solution was derivative of f with respect to y minus d by dx of derivative of f y prime is equal to 0. And when we saw this equation for the first time, our eyes lit up, right? Because we knew the other equation which looked very similar to this, which was this d by dt of del L by del q dot is equal to 0. And that means f is actually the Lagrangian, y is actually the generalized coordinate, and time. So x is actually the time, right? Means if we look at this functional, the functional j of q is integral of L dt. Okay, and this is generally called action. Okay, so uh, very general principle is that since Lagrangian is t minus u, if you throw a stone somewhere and it goes somewhere, it takes the path along which the average value of kinetic energy minus the potential energy is minimum. Okay, and you can think why this should be the case. Okay, so and this is called Hamiltonian's principle. Sorry, Hamilton's principle. Principle, which states that the real trajectory that takes place in the space is the one that minimizes the action. Okay. By the way, this was the taking off point for Feynman to develop the path integral formulation that he did for quantum mechanics. So, in case you study that in future, keep this in mind. Okay. So, more or less, that's what we did, right? And if you have multiple degrees of freedom, you can just do this for each of them. And same way, if you have multiple yi's, multiple functions, then you can use this equation for each of the degree of freedom. Okay, so that was the recap. Now let's look at some problems. So I don't have the copy pasted previous year's problems. So again, like last time, the problems were not from the content of this week. Nevertheless, I think it's my duty to solve them, and anyways, it's a good thing to solve physics problems in general. Okay, so all these problems were for calculating the principal moment of inertia. Calculate principal moment of inertia, right? The PMI for short. For the first one is a thin rod of mass m and length L. Okay, let, let me call it capital L. Okay. So what we have is a very thin rod, mass is L. Let's say this is x-axis, this is y-axis, and this is z-axis. So this is x, z, and y. Okay, so this is x is equal to plus L by 2. This is x is equal to minus L by 2. So the first thing is I along the x-axis would be simply 0, because all the masses are on the axis itself, so there is no distance from it. So the moment of inertia is clearly 0. Iy or Iz, both of them are equal because it's a symmetric object. So Iy, to calculate Iy, we need the distance of any mass dm from the y-axis, which is just x, right? So the moment of inertia is this distance x square times dm, right? Now we know that since it's a uniform rod, dm can be written as m by l, that is the density per unit length, mass per unit length, times dx. Right? So this becomes m by L integral x square dx, and x is running from minus L by 2 to L by 2. This becomes m by L and x cubed by 3 minus L by 2 to L by 2. So m by 3L and L by 2 cube minus L by 2 cube, right? And this is just m by 3L, and both of them are equal. Minus minus will get plus. So 2 times L cube by 8. So this becomes ml square by 12, which we know the moment of inertia of the thin rod, right? And again, because of the symmetry, it's same as IC. Okay. So these questions are there because they might be asked in the exam, and two, it's good to do some calculations also. There are many people who are good at physics conceptually, they understand things, but when it comes to hardcore calculations, algebra, they make a lot of mistakes. Okay, so the second one is uh, principal moment of inertia of a homogeneous sphere. Okay, so now we have a sphere, and it's a completely symmetric object. So, or the moment of inertia along any axis, we say, right? So, let me call this. This is x, and this is y. Okay, and any point would be given by r, theta, and phi. So, first thing we need to calculate. So we know that I am just calling it I because it's same along everything. It's just this distance, radial distance. Let me call it rho. Then it is rho square dm, right? So, and dm is the density, which is m by 4 by 3 pi r cube times the volume element dv. Okay, so we need to figure out one thing, which is rho is a function of r theta and phi, and dv as a function of r theta and phi, right? So the first thing, which is rho, is, let's say we are calculating about the z-axis because we are measuring theta along that. Then if this is r, then our rho is simply r times sine theta. Okay, so this is the first relation. The second thing, dv, is, we know in polar coordinates we have r square sine theta dr d theta d phi. Okay, so I is equal to integral of r square sine square theta, then dm is m by 4 by 3 pi r cube, and dv is r square sine theta dr d theta d phi. Okay, so I can pull out this constants, m by 4 by 3 pi r cube, and then the integral, which I was just writing as just one integral, but r is running from 0 to capital R, theta is running from 0 to pi. Yeah, it's the angle with z axis, so it can go from 0 to pi, and phi is running from 0 to 2 pi. Okay, and we have r to the power 4 sine cube theta and dr d theta d phi. Okay, and these are separable, so we can do r integral, theta integral, and phi integral, and the final result is product of all these three. So m by 4 by 3 pi r cube. Then r integral is integral of r to the power 4, which is r to the power 5 over 5 from 0 to r. Then theta integral, which we have to do separately, integral sine cube theta d theta, which is 0 to pi, yeah, and phi integral is just 0 to 2 pi d phi. Okay, now to calculate this integral 0 to pi sine cube theta d theta, we use, let's call this integral j, define sine theta is equal to, sorry, not sine theta but cos theta is equal to u. This is a very neat trick to evaluate such kind of integrals, so that sine square theta is 1 minus u square, and sine theta d theta is minus du, right? And now, so that now j becomes 0 to pi sine square theta, which is 1 minus u square, and sine theta d theta is just minus du. Okay, so this is equal to minus, and sorry, I should change the limits as well. So cos of 0, which is 1, so yeah, 1 to minus 1, so minus 1 to minus 1, and then we have 1 minus u square du, so minus integral of du, which is just u, from 1 to minus 1, and minus integral of u square, which is u cube by 3, again 1 to minus 1. So this is minus 2, and minus this is 2 by 3, right? Sorry, minus 2 by 3. So many minuses, so we have to be a bit careful. So this is simply 2 minus 2 by 3, which is 4 over 3. Okay, so this thing is 4 over 3. So our I, moment of inertia, becomes m by 4 pi by m by 4 by 3 pi r cube, then r to the power 5 by 5, 4 by 3 times 2 pi, right? Yes. Let's cancel out these terms. 4 and pi, r cube goes with r5 to have r square. These 3 gets cancelled, and at the end we have 2 by 5 mr square, right? You might have actually derived this in your 12th standard JEE preparation or NEET preparation using a different method, but once you learn polar coordinates, it becomes really simple. Okay, and the final question, third one, is PMI for a cylinder, solid cylinder, not a hollow one. Okay, so now we have cylinder of height h. So let's call this x-axis, this is z-axis, and this is y-axis. Okay, so clearly Iz is something different, but Iy and Ix are same because of this rotational symmetry, circular. Okay, so let's calculate Iz first because it's easy. Now we can label our coordinate. using rho, phi, and z, right? So in cylindrical coordinate, uh, this z is the height from xy plane, the z coordinate, and rho comma phi is, if you look at the projection from the above, just the polar coordinate in two dimensions. So phi would be this angle with respect to x-axis, and this distance is rho. Okay, so Iz is just integral of rho square, because that is the distance from z-axis. And now the volume element, which is again density m divided by pi r square h, and the radius is r. Okay, and then the volume element would be just the area element in 2D polar coordinates, which is rho d theta d rho, and then dz, right? So this becomes m by pi r square h. In rho we have rho cube d rho, where rho runs from 0 to r. Then theta, or oh, we are calling it phi, d phi, which runs from 0 to 2 pi, and dz, which runs from minus h over 2 to h over 2, right? Did I do that correct? Yes. Okay. So m over pi r square h, this integral is r to the power 4 upon 4. This is 2 pi times h, and this h gets cancelled. This 2 gets cancelled with 4. So you have half m r square. Okay. Pi's also get cancelled. So this is along the axis of the cylinder. It is half mr square. And that's not very surprising if you know that for a solid disk it is actually same thing, half mr square. And now you are stacking it on each of them. So the average distance from this z axis does not change. Okay. Okay. So the next thing, which is slightly trickier, is about x or y axis. Okay. So now you have to think of a point, how far this point is with respect to this axis. Okay, we'll call it y. So, and the way to do it is that vertically the distance is z, right? But then there is distance along the plane also, in the plane of xy is equal to whatever this is, z is equal to this thing. Okay, so if we look at projection from above, the point is somewhere here, where this is our y-axis and this angle is phi. So this distance, let's call this phi, so that this perpendicular distance becomes rho times sine phi. Okay, so that the total distance, which is, now if you imagine, this is z and this is rho sine phi, and the perpendicular distance is this much. What should we call it? Let's call it r. So r square is z square plus rho square sine square phi. Okay. So now this is integral of r square, which is z square plus rho square sine square phi, times dm, which was m by pi r square h, and the same volume element rho d phi d rho and dz. Okay. Again we have to put our calculus cap on and just work. So let me pull out this constant outside and call this I1 plus I2, right? I1 for this one, I2 for this integral. So I1 is just integral z square rho d phi d rho dz. So on z front it is from minus h over 2 to h over 2. Rho front it is from 0 to r, and on the phi front 0 to 2 pi. Okay, so this becomes h over 2 cube times 2, 1 over 3. This is r square over 2. This is 2 pi. Okay, so this becomes 1 over 12 h cube r square pi. Okay, and what about I2? Well, for I2, for r we have, okay, and z front just dz, r front we have rho square times this rho, so rho cube d rho, and phi is sine square phi. Sine square phi d phi. Rho is from 0 to r, and sine phi is from minus, sorry, 0 to 2 pi. Yeah. Okay, so this is just h times r to the power 4 by 4, and sine square phi is 1 minus cosine of 2 phi, right, upon 2. So integral of sine square phi 0 to 2 pi would be integral of half, which is 1 by 2 times 2 pi, minus integral of cosine 2 phi d phi 0 to 2 pi with a half. But we know that this is proportional to sine 2 phi, where phi is from 0 to 2 pi, which is just 0, because sine 0 is 0, sine 4 pi is also 0. Okay, so this term gets cancelled. So this entire thing is just pi. So pi. Okay, so this becomes h r to the power 4 by 4 pi. So the final ix or iy is m by pi r square h into 1 by 12 h cube r square pi plus h r to the power 4 by 4 pi. Okay, pi r square h can be cancelled. So pi r square, and this is square, and pi r square is just r square. So the final answer is m h square by 12 plus m r square by 4 ix and iy. Okay, so as you can see, the calculation can be a bit time taking. It's not difficult in terms of concepts, but you have to be very careful and practice a little bit. Okay, and that is one of the aims of this sessions. Okay, so I want to end with one final example on calculus of variation. It's not from assignment, but it's called what's the spelling? Brachistochrome. I had learned this problem earlier, but I did not know the name before today. So brachysto means short or shortest, and chron is time, chronology, right? So the problem is you start with some point x comma y, and you want to go to another point x1 comma y1, and you can go along any path, and there is a gravity g. Okay, then which path minimizes the time taken? Okay, so we can set up our coordinate axis that this is x and this is y. Then and if we start with at time t is equal to 0 at origin, then we can write that velocity at any point would be square root of 2gy, right? Just by from energy conservation. Okay, so the time taken, which is, if you consider a small section of this path, its length is some ds, so time taken is ds over speed v, and the total time is sum of all these bits. So in the limit of small ds, it becomes an integral. Okay, and we had calculated the formula for ds. The expression is square root of 1 plus y prime square, and this is times dx, and v is the square root of 2gy. Okay, so this is the function that we want to minimize, and one good thing is p. So this what should we call it? F, which in principle can be function of x, y, and y prime, does not depend on x explicitly. Okay, and whenever this integrand does not depend on x explicitly, which means just df by del x is 0, then we can use one identity for our Euler-Lagrangian equation, and that is that f minus y prime y prime is equal to c. So you get this relation where c is some constant. Okay, from the Euler-Lagrangian equation, using this fact, we can derive this one. Now, once you have it, let's put the value of f here, square root of 1 plus y prime square upon square root of 2gy minus y prime, and uh, derivative of f, this thing, with respect to y prime. So that becomes minus 1 over 2 square root of 1 plus y prime square and square root of 2gy. Okay, and this entire thing is some constant. And if you play with it, let's do it. So this becomes just cross multiplication. So 1 plus y prime square 2 times square root of 2gy minus y prime, actually plus square root of 2gy divided by 2 square root of 1 plus y prime square and 2gy. This entire thing is equal to constant. Okay, and this will lead us to the final answer, which is 1 plus y prime square, sorry, square is inside, times y is equal to 1 by 2gc square, which we can write as some k square. So this is the solution, the curve that will minimize the path, minimize the time. So if you have a straight road and let's say you have a ring, and calculate the time it takes for this ring when you drop the ring here and time it takes to reach this end, it will be some t1, right? Then you can think of a circle and that will take some time t2. But if you use this curve, which is by the way called cycloid, call it t3, that will be the minimum. In fact, any other curve will take longer time. So t3 is smallest. And last time we were talking about science museums and Foucault pendulum. This is also something that you often see in one of those. Okay, so and last thing, you can parametrically solve this solution. I'm just writing it down, but you can solve it. Is theta minus sine theta, and y is given as half k square 1 minus cos theta. And if you imagine a wheel that is rotating and moving along a horizontal plane, and then just fix a point, color it, and look at its path, then what it does is this kind of cycloid. Okay, so this is a cycloid motion, and very interestingly, it's the same curve that minimizes the time. Okay, so that's it from my end. This is all I had planned. Now, if you have any questions, please do ask. Anyone? Rakhu, Minakshi, Raj? Yes, Raj. Okay, if not, then we meet next week, same time, with content of week 11. Alright, enjoy, happy learn.